Today, we were strapping in for a high-speed tour of the silicon that is, well, basically running the modern world, AI accelerators. If you're watching the industry at all right now, you know AI is just defined by scale. We're talking massive neural networks, huge data sets, and computations happening at what our source material, this great guide on binary versus A, calls an industrial scale.
Right.
And the core problem is that this kind of math matrix multiplication just over and over and over is exactly what your normal general-purpose CPU is just terrible at.
It's just not built for it. It's slow, it's inefficient, and it would probably melt.
So our mission today is to give you a shortcut through all of this. We want to cut through the marketing jargon, understand what engineering characteristics actually matter, and learn how you can select the right class of hardware for any AI task.
Exactly. We're going to systematically explore the architecture, the key characteristics, and, the really crucial use cases for these devices, following the clear structure laid out in that guide. We want you to walk away knowing not just what they are, but why they represent such a fundamental shift in computing.
Okay, let's start with the basics then, the fundamental definition. If we want it in plain human language, what exactly is an AI accelerator?
The short version is pretty simple. It's specialized hardware built from the ground up to run AI workloads, especially neural networks, way, way faster and more efficiently than a CPU ever could.
So they're like co-processors.
Yeah.
They take the heaviest work, the training and inference, off the main processor's plate.
Right. And to really get why they exist, you have to understand why CPUs struggle so much. I mean, a general-purpose processor is built for sequential tasks. The article has this great analogy. It's like a careful chef handling one complex thing perfectly before moving to the next.
Yeah.
But neural nets, they don't need complexity. They need massive, relentless repetition, just millions of numbers multiplied at the same time. Asking a CPU to do that is like asking that careful chef to chop 10,000 identical onions.
They can do it, but it would take forever.
It would be agonizingly slow. An accelerator, on the other hand, is like 1,000 Sous-Chefs, all chopping in perfect parallel. That's all they do.
And to make this real for you, the guide offers a great summary of where these accelerators actually show up. And it's not just in some giant data center.
No, not at all.
I mean, think about the low-power inference that's constantly running on your phone for things like photo enhancement or your voice assistant. Then you have desktop workstations where people are running local LLMs, which demand really high throughput.
And of course, the data center, that's the big one, where you need the absolute highest bandwidth memory and massive capacity for training models.
But it goes all the way out to what people call the edge.
And that's critical. Edge devices, smart cameras, industrial sensors, they rely on these for real-time decisions, so you can avoid that lag of going to the cloud and back. The ultimate example is probably in a vehicle, right? Perception, planning, that needs incredibly tight latency for safety.
So if an accelerator doesn't do AI, but just does the math, what math are we actually talking about here?
The functional truth is it's just pure linear algebra. I mean, at its core, an accelerator is a high-volume factory for matrix multiplication. That's it. It just repeats that billions of times a second.
And inside a transformer model, every attention head, every block, it's all just that.
It's all just a linear algebra factory, exactly.
Which means the accelerator really has two jobs. The first is the obvious one. Compute those tensor operations and do it fast and in parallel.
Right. But the second half, and this is the one people always underestimate, is moving data efficiently. This is the whole ball game. You can have the world's fastest compute engine, but it's a paperweight if it can't get the model weights and the input data fast enough to stay busy. The source material calls this the compute plus data loop. That's the entire efficiency battle.
That's a perfect lead-in to the 6 key engineering characteristics that really define these devices. This goes way beyond the one marketing number you see on a spec sheet.
Right.
So first up, parallel compute units. This is the foundation. More cores, tensor engines, whatever they call them. You need to run a huge number of small operations at the same time. Sheer muscle.
And second, memory bandwidth. This is the Achilles heel for so many applications. The guide really stresses this. If your model is memory-bound, meaning it can't get data fast enough,
all that extra compute is just sitting there, useless.
Exactly. The bandwidth decides if your accelerator is sprinting or stuck in traffic.
Okay. Third is precision support. And this is a really clever efficiency hack. We've moved away from the standard 32-bit floats that CPUs use. We're talking about lower precision like FP16 or even INT8.
And it's good enough numerically because for inference, The model weights are already fixed. You don't need all that precision you needed for training, so you can drop to 16-bit or 8-bit, which takes less power, less silicon, and you don't really lose much accuracy in the final result.
Wildly better throughput.
Wildly better. Then you have Interconnect. This is how all these chips talk to each other inside a server. Think of it like a high-speed highway system.
And across a whole cluster of servers, it needs to act like one giant unified machine.
Right, to avoid what they call the synchronization tax during training. Fifth is the software stack. This is so important. It's not an accessory. The guide calls it a critical part of the architecture. Drivers, compilers, optimizers.
Because if the software can't use the hardware efficiently,
then the raw performance of the silicon is just wasted. The software is what unlocks the hardware.
And finally, number 6, power and thermals. I mean, at a data center scale, performance per watt is king.
It's often the ultimate metric. It's the difference between a solution you can actually deploy and something that's just a science project because it would melt the building.
So now we know the components. Let's look at the actual products. What are the major families of chips that fall under this AI accelerator label?
There are really 5 major families, and they exist on a spectrum from flexible to highly optimized.
Okay.
First, you have GPUs, general parallel processors. They're the default because they're flexible, they scale, and they have a really mature software ecosystem.
And then the more specialized stuff.
Right, like TPUs, Google's custom chips. They are ASICs, application-specific integrated circuits, tuned specifically for matrix math at a massive scale inside their cloud. They trade flexibility for raw, specialized speed.
And then the smaller ones, the NPUs.
Neural processing units. These are small, power-focused cores you find on device. In your phone, your laptop. Their main job is efficiency and a tight power budget.
And then there were FPGAs?
FPGAs, yeah, field programmable gate arrays. These are fascinating because you can reconfigure their logic. They're slower to program, but you get super low latency, and you can actually update the hardware's behavior with firmware.
And the last one.
Dedicated ASICs. These are the most extreme. Purpose-built for one specific job, trading away basically all flexibility for maximum efficiency and speed.
Which brings us to the classic confusing question.
Yeah.
Is a GPU an AI accelerator?
Yeah.
The guide is very clear. Yes, absolutely. A modern GPU is fundamentally an AI accelerator because it's brilliant at the massive parallel compute these workloads need.
Exactly. What people really mean when they try to draw that line is they're comparing general-purpose GPUs against the non-GPU accelerators, the TPUs, the NPUs, the really specialized stuff.
So it's not the chip, it's the whole system you're comparing.
It's the whole system, the tool chain, the memory, the interconnects, how mature the whole platform is. The platform is what really matters.
Okay, let's get into the mechanics. The article suggests a simple 3-step mental model for how they work. Step 1 is compute. Multiply, add, apply an activation function, and then just repeat that a billion times.
Step 2, move the data, fetch the weights, stream the inputs.
And step 3, this is the clever part, hide latency. You overlap the data transfers with the compute, so the execution units never have to wait. They're always busy.
And that's where that reduced precision hack comes back in. If you drop to 16-bit or 8-bit, you can do 2 to 4 times more operations in the same clock cycle. It's a massive boost.
Okay, let's go one level deeper into the architecture, because this is where all the jargon lives. We can break it down into 4 layers.
Sure. First, you've got the compute tiles. These are the actual silicon elements. On a GPU, they're called tensor cores. On a specialized chip, you might hear the term systolic array.
Which is what?
Think of a systolic array as a perfectly organized assembly line. Data flows in one end, results flow out the other, and it's designed for one thing, churning out matrix math at maximum speed.
Got it. Second layer.
The memory hierarchy. This is organized from super fast on-chip caches, engineers call them scratch pads, down to fast external memory like HBM, which is stacked right next to the processor die. The whole goal is to minimize expensive trips off-chip.
But if they have to go off-chip, they need the interconnect.
Exactly. Within a machine that avoids the synchronization tax. Across a whole cluster, it needs to be so fast and predictable, it's almost like an extension of the chip's own memory.
And the final layer, we're back to this again, software as architecture.
It's that important. It's a critical warning. If the compiler can't optimize the sequence of operations, the silicon's potential is just gone. A great sheet with bad software feels sluggish.
Okay, let's talk about the spec sheets. TOPS versus TFLOPS. The guide says they're not lies, but they're incomplete truths.
That is a perfect way to put it. TOPS, tera operations per second, almost always means low precision integer math, like INT8. TFLOPS, tera floating point operations, usually means FP16 or FP32.
And why is that misleading?
Because they rarely tell you the memory bandwidth needed to actually sustain that number. A chip might theoretically hit 1002 PS, but if the memory can only feed it enough data for 500, then the other 500 TOPS are just wasted potential.
So for you, the listener, who might be buying this hardware, what's a better checklist?
You have to treat the spec sheet like a curated resume. Look past the headline number, investigate the effective memory bandwidth, check what precisions are supported, is cutting-edge FP8 there, and crucially, does the model you want to run actually fit in the VRAM?
Right. VRAM is the real currency for local models.
It is, and we see these trade-offs everywhere. In data center training, you need scale and stability, so that's where the massive GPUs and TPUs live.
But data center inference is a completely different problem.
Totally different. It's all about cost per token, batching efficiency, tail latency, and that's often where specialized non-GPU hardware can win, not on raw speed, but on watts and dollars.
And then for local AI on a PC, privacy is a driver, and as you said, VRAM is everything.
And for edge vision and robotics, it's all about low latency and power efficiency, avoiding that round trip to the cloud.
That diversity explains all the different vendors we see.
For sure. You've got platform owners like Google building TPUs for themselves. You've got the merchant silicon vendors, NVIDIA, AMD, Intel selling to everyone, and they win with their software ecosystems.
Speaking of AMD AI accelerators, the guide makes a good point that their success isn't about raw compute slogans.
Not at all. It's about how well their software stack and their interconnect strategy fit into a workflow developers are actually using.
Oh.
If the software isn't there, the silicon just sits on the shelf.
Okay, let's clarify one more thing for people working on their own machines. We hear about integrated NPUs versus discrete PC AI accelerators. Discrete just means it's a separate card, right?
Yeah, not baked into the CPU package. And the trade-off is pretty clear. The integrated NPU is great for sipping power on everyday background tasks. A discrete accelerator card is all about sustained throughput for heavy models, and it brings that big chunk of dedicated memory that the local LLM scene demands right now.
But discrete cards aren't always the answer.
No. They win when the workload is predictable and you can keep them fed. They lose when you need a broad ecosystem and compatibility with every new model architecture you download from the internet.
So that brings us to the big takeaway. How do you choose the best AI accelerator?
The answer is that best is a trap. It's a meaningless word without context. The best choice depends entirely on your workload.
You have to start by defining the bottleneck. Is it training or inference? Throughput or latency?
Exactly. Measure the constraint, not the marketing logo. If you're memory bound, you buy bandwidth and VRAM. If you're latency bound, you look at how it handles tiny batches. If you're ops bound, you buy mature tooling.
And the guide points out 3 huge mistakes to avoid.
1, buying TOPS or TFLOPS instead of buying a complete system. 2, ignoring the software stack. And 3, a classic, chronically underestimating memory, bandwidth, and the cost of moving data.
So here's the real punchline from this whole analysis. The winner is not the chip with the highest number. The winner is the system, the hardware and the software together that reliably delivers what you need, whether that's tokens per second or inferences per dollar, at a cost and power level you can actually live with.
That's it. You have to see the accelerator as just one part of a complete system. And often, VRAM, bandwidth, and software are way more important than raw compute speed.
So if you take one piece of advice from this, let it be this. Stop chasing shiny numbers on a spec sheet. Pick the one workload that actually matters to you. Run a small end-to-end benchmark and profile exactly where the time is going.
And then you choose the class of hardware that's built to attack that specific bottleneck. Don't let the spec sheet choose for you.
A perfect place to wrap up the practical advice.
And this raises one last, bigger question for you to think about. Given how absolutely vital the software compiler and the kernel libraries are, the silicon is basically useless without the code, how much does our dependence on a single vendor's proprietary software stack influence what the next generation of AI hardware will even look like? Should the industry be optimizing for open toolchains to break that vendor lock-in, rather than just chasing more specialized, closed-off silicon? Something to chew on.